Actions of probability. Now, when we're talking about probability, we're actually talking about a probabilistic experiment, because we need to be able to conduct an experiment to find out the probability of its results, So when we talk about a probabilistic experiment, we are talking about some kind of an, experiment that involves uncertainty, like tossing a coin or, I don't know, rolling a dice or something like that. It has to be unknown. The outcome should be unknown. We should not be able to guess it, not guess it, but know it beforehand. We may guess it successfully, of course, but knowing it just, removes uncertainty. So as long as there's uncertainty, we can talk about a probabilistic experiment. So any experiment we are talking about in this class is a probabilistic experiment. So it will not be, deterministic. We will not know what's going on. We will all, treat them all like stochastic experiments. So we also have sample space and events. These are simple definitions of stuff that we are going to use in probability. The sample space is a set of all possible outcomes. Now, when we're talking about all possible outcomes, it can be infinitely many or just finite stuff, but still all possible outcomes. So, for example, when we're talking about the sex of a newborn child, we have two different outcomes. It's either a boy or a girl. Or when we're talking about, let's talk about a race, for example, and there are 7 athletes in it, and the order of finishing, who is the first, who is the second, who is the last, etc. It's a set of all the results. So it's 7 factorial. And now we can be talking about flipping coins, 2 of them at the same time. So it's either heads or tails with 1 coin. But when you're talking about 2 coins, you get 2 times 2, because you can have 2 heads, a head and a tail and a head. The coins can have, different outcomes, or 2 tails. So when you think about it like that, when you're making an experiment, if you can find all the elements, all the outcomes, if you are talking about all the outcomes, you're talking about the sample space. And the sample space is very integral, is very important in probability, because it's how we, calculate the probability of events using the number of elements in the sample space, which we'll see soon enough. There's also events. Yeah, I said events. So what's an event? An event is a subset of the sample space. So the sample space is all the outcomes in an experiment. An event is some of these outcomes. Maybe we can take an event that's also equal to the sample space, so it can be all the outcomes, or it can be an empty set. Okay, an empty set is a subset as well. So the event might be infeasible. It might be an empty set. So there are no outcomes that satisfy that event. So when we're talking about events, we are talking about a subset of the sample space. Now, for example, there can be an event where the newborn child is a girl. So it's only the outcome is the G outcome, that's it. Or we can say that the third athlete has won the race. So we are talking about all the other outcomes, which is like 6 factorial outcomes, because we already know that the third one is placed in the first rank. So the other remaining 6 athletes will be in any of the other ranks. So it's 6 factorial. Or we can be talking about the event that head has appeared first on those 2 coins. So it might be a head or head-tail. So there are 2 outcomes, 2 elements in that event. So when we are talking about sample space and events, we're actually talking about sets. So probability theory is extremely close to set theory. It's, it uses a lot of its foundations from set theory. So you will see some similarities, a lot of similarities actually, with set theory and probability theory. You've already seen it in this one, in this slide, and you will see them in the other slides as well, in the following slides as well. Now, we have union and intersection of events. This is the same as the union and intersection of sets. So when we're talking about the union of events, we are talking about at least 2 events where they can be shown like this, E union F. And this union consists of all the elements, all the outcomes that was in either E or F. So this new outcome, this new event is called the union of E and F. We all know that. And this will occur, this union will occur if any of the outcomes, if any of the if any of the sets E on F or events E on or F occur. So we already know that from set theory. The same can be said about intersection. When we're talking about the intersection of two events, we can write it like this, EF or E intersection F. They're both applicable. So, and we read it as intersection of E and F. This EF event will only occur if both of those events occur. So we have to find an outcome that is both in E and F. If that outcome happens, if that outcome occurs, then the intersection will occur. Otherwise, it won't. And then there's the complement of an event, which is like a complement of a set, the same thing actually. So for any event E, for any event we can think of, we can define the complement of E. Now, the complement of E consists of all the outcomes in S, in the sample space, that are not in E. So it's actually the same thing. When we were talking about the set theory, when we were talking about set, it was all the elements that was not in the set. Now we're talking about all the outcomes, which are elements by themselves, that are not in the event we have defined. So the complementary of E, as you can see here, is every other area outside of E, every area outside of E. And there's the mutually exclusive events. Now, this is the same as mutually exclusive sets as well. When we're talking about mutually exclusive events, we are talking about two events that don't have any common outcome. So they actually have no intersection points. So their intersection is just a, zero. It's an empty subset. It's an empty set. There is no intersection. So they are called mutually exclusive events. Now, we also have the same rules that apply to sets applying to events. We have the commutative rules. So E and F, either in union or intersection, they can change places. The associative rules, the parentheses can move. For example, if we are trying to union three events, we don't care if we take the union of E and F first and then take the union of G on top of it, or start with F and G and take the union of them and then add E to them. It will give the same answer. It's the same for intersection as well. We can move the parentheses to the other side. We don't care which events we intersect first. And then there's a distributive property. Now, this property, as you can remember from the set theory, is very, easy to understand, but not that easy to apply sometimes. So as you can see, we have the union of E and F, which is intersected by G, which means that we can take this G outside of the parentheses and throw it inside and just, have it merge with the events inside to get rid of the parentheses. So instead of writing E union F, which is intersected by G, we can write E intersected by G, E and G intersection, union F and G intersection. Now, we can see that this is the same as the sets as well, which is normal. And here, on the other side, we can see that the parenthesis contains an intersection and the union is outside the parenthesis. And this union can be, sent into the parenthesis as well. So we have E union G, which will be intersected by F union G. You can see the shaded areas for these, simple stuff, but still, these are the same rules that govern the sets, which is why I said the probability theory takes its, roots from the set theory as well. Now, we also have De Morgan's law. Now, you may have forgotten this, but I'm pretty sure you have seen this in set theory as well. But this is, again, a simple, simple enough to remember, but not that simple to use rule. We say that when we have different events, EI, from 1 to n different events, and we are trying to union them, and then get the complementary of that union. Instead of doing that, you can take the complementary of all the events and just intersect them. So this complementary is actually being sent into the parentheses and changing everything, changing the operation from union to intersection, changing the event from normal to complementary sets. So you can just send the send the complement action, operation, whatever, inside, and then get this result. It's the same if the role were reversed. So instead of the union operation, if you had the intersection operation, and if you wanted to send the C value, the C action, C operator inside the parentheses, the complementary operator inside the parentheses, then you would get the union instead of intersection when going outside, but you would be getting the union of all the complementary events inside the parentheses actually. De Morgan's laws are used a lot, but you know, it depends on from question to question, which you will see later on. Now, so what's the definition of probability? We have seen everything about the set theory, the relations between them. Now, let's start with an experiment again. So we have a sample space S. We don't know the largest of the sample space. We may have many outcomes or very little outcome. It doesn't really matter, number of outcomes, but still, we have an experiment with a simple sample space S. And we start doing this experiment repeatedly. So let's start with a roll of a die. When we roll a die, we have 6 different outcomes from 1 to 6. So we are rolling the die repeatedly. So there's an event in the sample space S, and I will just pick an event for the die. Let's say that the outcome of the die should be 2 or lower. Okay, so 2 outcomes actually satisfy this event, 1 and 2. 3, 4, 5, and 6 do not satisfy this event. So if you want to find the probability of this E, we make some, we conduct those experiments repeatedly up to a certain point, up to an N, and then just count how many times the event has occurred. So how many times did I get a 1 or 2? For example, I have rolled the dice 100 times, and I get, I don't know, 30 times 1 or 2. So 100 times the experiment has been conducted, and 30 times I have been successful. So my success rate is 30 over 100. So it's like 0.3. So I can just say, oh, okay, my event is a probability of 0.3. But this limited number is not enough. So this N should not be 100, but it should be into infinity. Why so? Because we are talking about the probability of an event, okay? But we are also talking about experiments and finite experiments. So if you make finite experiments, we may get errors. For example, we already know that when we roll a die, the probability of 1 coming up is 1 over 6. It's easy because if the die is fair, if there are no loads in it, and if it comes up 1 and 2 and 3 and 4 and 5 and 6 with the same probability, then the probability of getting 1 is 1 over 6. We already know that. But we start conducting experiments. I have rolled the die 1 time and I get a 5. And I'm done. I'm not conducting any more experiments. So is the probability of getting 5 1? Or is the probability of getting 1 0? No, it's not. I already know that it's 1 over 6. I just conducted an experiment and I get a 5. So no, I cannot stop that. I should keep going. So I roll again, I get a 3. So is the probability 1 over 2 for getting a 3 or a 5? No, it's not. It should be 1 over 6. So I keep going. I have to conduct this experiment a lot of more times. For example, I got to 600 times. I have rolled the dice 600 times. And I got 590 times out of this. Okay, 90 out of 600. It's close to 1 over 6, but it's still not 1 over 6. It might have been 100 times. I might have been lucky, but that is very unlikely. I cannot get 100 out of 600 for all the, all the faces of the die, all the sides of the die. It's probable. Yeah, it's possible, but not probable. Because you will probably get 101 times of 6 or 98 times of 2, etc. There will be errors, small errors in that all the time. There might even be big errors, something to work on. But still, I can keep rolling the dice. If I roll it to infinity, then I will get the probability of 1 over 6. So experimenting is okay, but you need to do it infinitely to get the right result. So it's like the occurrence frequency. I'm just rolling the dice and I'm trying to keep track of how many times I have rolled a certain number to find the probability of that number. So when I am at 100 rolls, I check the number of 5s I have rolled. It's 17. Okay, 17 out of 100. That's okay. And I keep rolling. I'm at 600 rolls, and now it's at 105 successes for 5. So when I check this you know, okay, 105 out of 6. And I keep going, at 6,000, at 600,000, at 6 billion, at 6 trillion, etc. I just keep checking how many times I get a certain number. And every time you will get a different probability, because every time something will change. Every time you roll, something will change. So you can get 2 or 3 times the same probability or more, but still at 600,000 maybe rolls, you don't have to, you know, you shouldn't expect to get the same result every time. It will keep changing. But at infinity, it's just one number, one probability. So we are actually talking about taking this n, taking this number of experiments to infinity. But of course, we don't need to take this n to infinity to know something with certainty. As I said, with a die, there are 6 sizes. So we already know that any side has a probability of 1/6, because they all have the same, probability. They should all have the same probability, because the die is expected to be fair. So as long as it's not loaded, it should be 1/6. But there's also some other definition of probability, something that's not very mathematical like this one. It's called a measure of belief. So for example, today is a bit overcast in Istanbul. So I'm just going to say that, oh, okay, it might rain today. It's not very likely, but there's a 30% possibility of raining in Istanbul today after this hour. It might have already rained in the morning, but for this hour till, I don't know, evening, 6, 7, 8, etc., I can just say that, oh, okay, there's a 30% probability of raining. Did I conduct an experiment? Did I go into the future, check the weather and come back? No, I don't really know what's going to happen. I cannot conduct that experiment. But I can just say that, okay, I have seen this weather before. I know how Istanbul behaves, how the weather changes. So this is my measure of belief. I believe that it's going to rain with 30%, 30% probability, because I have already seen similar weather conditions before. This is my measure of belief. It comes from past knowledge, not by conducting this experiment, but experiments that have already been conducted beforehand and were similar to this one. Because this experiment I cannot conduct. As I said, I cannot go into the future, check the weather and come back. It's not possible. So I have to form a belief about this one. So measure of belief is also a probability. Okay. So what are the axioms of probability? When we're talking about axioms, we are talking about the foundations. Okay. These things are assumed or accepted as true. You cannot change these. These are the foundation of probability. First one, and the most important one in my opinion, that is any event has a probability between 0 and 1, 0 and 1 included. This means that we cannot find any probability value less than 0 or greater than 1. If we are doing something like this, we are doing it wrong. This is the same for your exam, by the way. When you're solving a question, if you find a probability that is greater than 1 or less than 0, try to correct your answer, whether it's reasoning or just a miscalculation. If you cannot do it, if you don't have the time, make sure that you write a note or something like that, saying that you already know that this cannot be, greater than 1 or less than 0, because otherwise I will assume that you have come to the conclusion that the probability should be greater than 1 or less than 0, and you will get 0 points from that question. However, through your, way maybe, if you find an answer that's not between 0 and 1, for probability at least, then you may get a 0 from that answer, unless you explain yourself. The reason you cannot, correct that mistake. The other axiom is the sample space has a probability of 1. Well, it's to be expected because the sample space has all the outcomes. So when we make an experiment, when we conduct an experiment, the outcome should be inside the sample space. So the sample space has a probability of 1. And then the third one, for any sequence of mutually exclusive events. Now, if they are mutually exclusive, then they don't have any common outcome, which means that we can just, when we are talking about, getting a union of them and then getting the probability of that union, we can just say that, okay, instead of getting the greater set and dealing with the greater set, we can just find all the probability values for those events and just sum them. So instead of getting a union, you can get a sum of probabilities. This is the same thing. So which one is easier? It will depend on the question, of course. So rolling of a fair dice, that's a very simple example, and we have already talked about it. When we roll a dice, the outcomes are 1, 2, 3, 4, 5, 6, and they all have the same probability, which is 1 over 6. When you're talking about an event where you can get the odd numbers, okay? When you roll a dice, what's the probability of getting an odd number? So we are talking about 1, 3, and 5, which has a probability of 1 over 6 plus 1 over 6 plus 1 over 6, which is 1 over 2. So we are talking about events, and these events are mutually exclusive, because if I get a 1, I cannot get a 2 on the same roll. Okay, so they are all mutually exclusive. If you get a 1, you cannot get a 2. If you get a 2, you cannot get a 3, etc. And the propositions. Now, these are, again, the same propositions that we actually use in the set theory. So you already know these, but they are just applied to probability. For example, the probability of complementary of E is equal to 1 minus probability of E. Now, this actually in set theory was done with number of elements in a set. So, for example, if the sample space had 15 elements and the set has set A had 5 elements, then the A complementary would have 10 elements, because their total should have to be equal to the sample space. Now, in here, 1 is actually the probability of sample space. So we can just write, let's write it, instead of 1, we can just write PS. So we already know that PS is equal to P of E, couldn't write equal to P of E plus P of E complementary. This is the same thing, okay? So it's actually the same thing in set theory as well, with elements instead of probability. The second proposition says that if event E is a subset of event F, or sub-event of event F, because it's a subset, so then E cannot have probability greater than F. Okay, PE should be less than or equal to PF, which means that E cannot have a greater probability than F, which is to be expected, because if E is a subset of F, it can at most be equal to F, or it can have less outcomes, which means that it will have a lesser probability. Again, with E union F, the third proposition, we have PE plus PF minus PEF. Now, this is again from set theory. You can remember the number of elements from union. So if you had A union B, number of elements of A union B, you will be looking at the number of elements in A plus number of elements in B minus number of elements in the intersection. This is the same thing again from set theory. And the last one is the generalized version of the third one. And we are gonna see it at most for 3, I guess, maybe very, very, very unlikely with 4 of them, but still third is the limit normally. So when you take the union of 3 sets or 3 events, for example, ABC, union of ABC, you are talking about, when we're talking about union of ABC, probability of union of ABC, of course, you're actually talking about, let's write them so that we can see it easier. The probability A, let's say U, B, C. Now we are actually talking about probability of A plus probability of B plus probability of C minus probability of AB. Should have been capital. Minus probability of AC minus probability of BC plus probability of ABC. Now, this version you should remember from high school, I guess. It's again from set theory. Instead of number of elements, we're using probability once again. Now, if we, this is the general form, of course. If we take this into the next step, if we had 4 of them, 4 elements, then we would have to write A plus B plus C plus D minus AB, AC, AD minus, again, BC, BD, and minus CD plus ABC, BCD, ACD, and anything else? A, B, D, yeah, stuff like that. So we would actually have to, write more and more sets, probability sets in there. But still, this is the general form. Fortran is the general form, so you can remember it easily. It's plus, minus, and the number of elements, number of events inside the probability bracket is just increasing by 1 each iteration. So, what about an example? If 3 balls are randomly drawn from a ball containing 6 white and 5 black balls, what's the probability that one of the drawn balls is white and the other 2 is black? Now, this is a straightforward probability question. So we have 3 balls to choose from 11 balls. 11 balls, 6 of which is white and 5 of which is black. So we are talking about the probability that one of the drawn balls is white and the other 2 is black. Now, when we are talking about experiments like this, there are usually more than one way of looking at things. For example, this is drawing balls from an urn, okay, from a ball urn. I can be drawing these balls one by one without replacement, or I can be drawing them 3 at the same time. This is both the same experiment done differently. So you can be picking your balls one by one without replacement, just picking them out, putting them out, and after the third one you just stop. Or you can be taking all 3 of them at the same time. These are both the same things, but they are calculated differently. The probability values are calculated differently, but the probability values are, of course, the same. They will be equal. Let's start with the first one. Let's say we are picking them one by one. Now, I have 3 balls to pick, and I want one of them to be white and the 2 of them to be black. So I can pick those balls in this order: white, black, black, okay? Or black, white, black, or black, black, white. Okay, I need to calculate 3 different experiments, 3 different ways of doing this experiment, and I need to sum their probabilities. Let's start with white, black, black. Now, when I'm picking the first ball, there are 6 balls in there, and my probability of getting a white ball, sorry, there are 11 balls in there, and my probability of getting a white ball is 6/11, because I have 6 balls in there from a total of 11 balls. So my first move to get a white ball has a probability of 6/11, 6/11. Now, after I have put the white ball aside, now I have 5 whites and 5 black balls in there. Okay, now I'm trying to pick a black ball, which is 5/10, 5/10. Now I have 4 black balls left out of 9 balls, and I want to pick another black one because it was white, black, black. So I'm going in and picking another black, which is a probability of 4/9. So my total probability for this order, white, black, black, is 6/11 times 5/10 times 4/9. Now, if we do this experiment for the 2 other ways, for black, white, black, like this, or black, black, white, we will get the same results. 120/990. Now, when we add these 3 together, we get 360/990. We get 4/11. After simplifying them, we get 4/11. Now, this is the first way of experimenting, of doing this experiment. The second way is just picking them at the same time. Okay, I'm trying to pick 3 balls out of 11 balls. So my sample space is 11, 3. The combination of 11 of 3, 3 of 11. And then I'm trying to pick the only white ball out of 6 balls. So 1 out of 6. And then I'm trying to pick 2 black balls from 5 balls. So 2 out of 5. When I calculate these combinations, again, I will get 4/11. The same result that the first way had offered me. So, which is to be expected. We were already expecting it to be like that. So we can pick which way we are going to use to solve the question. But there are some, situations where you cannot use one of those ways because it's too hard to calculate. It might be very, chaotic or very complex in there using one of those ways. So it's okay to just pick one of those 2 ways and focus on that one and learn it well, but the other one should be, general knowledge to you as well. So what are you going to use? You're going to use the, simple probabilistic expressions like the first one, or are you going to use the combination way? They are both okay. They can both be used in most of the situations, but in some situations, you may have to use one of them because it will be much more easier to use. For example, in this one, the second one is easier to calculate. It looks like it is because it's, requires less space, but it might surprise you. It's combinations. It's going to need lots of factorial values in that. They might simplify and it might be an easy answer, but you may never know. The first one looks easy as well because it gets the same result all the time. So it's just 3 times 120. So it's easy to simplify. But still, if you make a mistake in one of those, because you are, trying to multiply a lot of values at the same time, you may make a mistake in one of those. So if you're prone to mistakes, this is harder than the combination value, maybe. As I said, it depends on you. The third one. Now, this example is a good example of why this course is a bit harder than other courses, because as you can see, there's a question here, there's an example here with no numbers. So we may see lots of questions like that. We don't need numbers to be able to calculate probabilities, as you can see here. N contains n balls, of which one is special. Okay, there's a number there, 1. If k of these balls are drawn, one at a time, with each selection being equally likely to be any of the balls that remain at the time, what's the probability that the special ball is chosen? Now, in this example, think about the 2 ways we have seen in the previous example. If you try to calculate the probability every step of the way, now you're going to make n selections. So you have to calculate n different scenarios. For example, scenario 1, I picked a special ball in the first draw. Okay. Scenario 2, I picked a special ball in the second draw. Okay. Scenario 3, I picked a special ball in the fourth try. Okay. The 6th trial, the 10th trial, the nth trial. Okay. So I have to calculate a lot of different scenarios and I have to sum them later on. Not possible. I mean, it's possible, of course, but not logical to do it like that because it's going to take a lot of time unless I can come up with a series that can, just simplify itself. But still hard, not that easy. On the other hand, if I go with the combination way, it might be easier. I'm trying to pick one special ball out of one special ball. Okay, 1 of 1. And then I'm trying to pick k minus 1 non-special balls, normal balls, out of n minus 1 normal balls. So k minus 1 out of n minus 1. Okay. The total number of ways I could have done this. Okay, I had n balls and picking k balls, so k of n. I'm just going to write the combination like this. And then I will just open the combination, use the factorials, just use the formula for combination, and use the factorials and simplify them, and I will get k over n. Okay, this is too easy. A very simple answer to a very complicated looking question. That happens all the time. So,
hocam, sınavda bu faktöriyeli açmazsak hani puan kırılır mı ya da hani yanlış mı olur?
If you don't simplify this, you would lose points, but not that much. But think about it like this. When you are faced with a problem, you have to simplify it as much as possible with the solution because it's easier for your, professors to understand it. Okay, so we can give you better marks, higher marks, because if you leave it very complicated, if you don't understand, or it is probably wrong, because if you can simplify it, you cannot expect us to simplify it for you as well. So if it's very complicated, okay, it looks wrong, it should be wrong, then you can get low points. But if you can simplify it, it's better. Also, this is a very good question because there are sometimes when you find, answers with lots of, let's say, letters and stuff like this, and it looks very complicated, but it can be simplified or it can at least be understood somehow, and you just leave it like that. And then somehow, when I first see it, I can just say, okay, this is greater than 1. For some reason, if I can see it at that point, and if I say it's greater than 1, if it will be simplified and it will be greater than 1, and just mark it 0 because it's greater than 1. You cannot find probability greater than 1. So simplify it to see if you are in the range at least between 0 and 1. For example, k over n, it's in the range because we know that n is greater than k already. So there are no problems there. Okay. So example 4. If n people are present in a room, what's the probability that no two of them celebrate their birthday on the same day of the year? How large need n be so that this probability is less than 1 over 2? Okay, normally we do this in the class, and I ask everyone their birthdays. We start with people in January, people in February, and we get some same day birthdays, some hits in that, in that lesson, but it's not possible here, at least not now. So we're gonna have to think of it ourselves. So, for example, I'm alone in the room. Someone else enters the room. What's the probability that that person has the same birthday as me? Well, I have a birthday in one of 365 days, so it's 1 over 365 for me. But when he enters or she enters, for her, birthday to be the same as mine, it's 1 over 365. Nice. What about it being different? Okay, what's the probability of her or him having a different birthday? Well, it's 1 minus 1 over 365, so it's 364 over 365. Okay, so he or she has a different birthday. Sits down as well. Another person comes in. Okay, now what's the probability that he has a different birthday from both of us? Okay, it's 1 minus our birthdays, 1 plus 2, 1 plus 1, which is 2 different birthdays. So it's 363 over 365. It goes on like this till the nth person comes, which makes the probability like this. Now, this is me sitting alone. Okay, I have the same birthday as myself, so I'm not going to check anything. I don't need to check this one. When someone else comes, first person comes, this one. Second person comes, this one. Nth person comes, this one. So we need to pick n large so that this probability is less than 1 over 2. As you can see, the probability starts with 1. It's very close to 1, but it gets as as the new values get multiplied, it gets smaller and smaller. So it should be less than 1 over 2. So you need to conduct 23. You need to have 23 people in the house or in the room to make sure that any two of them can have, a common birthday with a probability greater than 1 over 2. Because this is not having the same birthday, which is less than 1 over 2. So we are talking about greater than 1 over 2 when we're talking about having the same birthday. Another example. Well, this one is a bit...
Ben bir soru sorabilir miyim buna geçmeden önce?
Of course.
Bir önceki soruyu kombinasyon metoduyla çözmemizin bir yöntemi var mıydı?
Not that I'm aware of with n people. Because it would take a lot of calculations, I guess. I would say no. Maybe there is, that one I cannot think of right now. But as far as I'm concerned right now, it's no. Now, another example. This one is a bit more complex because it requires a bit, outside of box thinking, I would say. But you will see what I'm talking about. Now, a football team consists of 20 offensive and 20 defensive players. Okay, this is American football, of course, offensive and defensive players. The players are to be paired in groups of 2 for the purpose of determining roommates. Okay, now we are trying to pick people and group them 2 by 2. All right. If the pairing is done at random, all right, what's the probability that there are no offensive defensive roommate pairs? Now it says that we are picking at random, all right, and we don't want any offensive defensive roommate pairs. So all offensive players should stay together in 10 rooms, 2 offensive players in each room, and all defensive players should stay together as well, 2 by 2. Now we're going to have to calculate the number of ways we can just distribute those 40 players in 20 rooms, 2 by 2. Now, in here, the rooms themselves aren't important, so the order shouldn't be important. It's just the way they are classified. That's the important part. So, we'll start with the offensive players or defensive players, it doesn't really matter, but we'll start with the whole 40 of them. Now, when we have 40 items, let's call them, and we want to separate them 2 by 2, we can just use a multinomial formula. So we can just say, let's get to the answer. We can use this one. 40, 2, 2, 2, 2, 2, 2, etc. Now, this one is calculated like this, 40 factorial over 2 factorial to the power of 20. Now, this one is the number of ways we can divide all these 40 players into 20 pairs, but they are ordered. So I pick 2 people, 2 players first and put them in the first room. Then I put 2 others and put them in the second room, and etc. This is an ordered version. I don't need an ordered version. I don't want an ordered version. Any order is fine as long as the players are in the same room together. For example, let's start with 4 different players, 1, 2, 3, 4. We have only 4 players. Now, we're going to put them in rooms. So I can pick 1 and 2 together and 3 and 4 together. 1 and 2 is in the first room, 3 and 4 is in the second room. Okay. Or I could have picked 3 and 4 together and 1 and 2 together. It's the same thing, but I've changed the order. It doesn't matter. The outcome is the same. The outcome is the unordered versions, because we are only talking about pairs. We are not talking about which room they are. We don't care about which room they are in. Okay, we are only talking about the pairs. So I don't care where they are. So I'm gonna have to remove that order from this outcome, number of outcomes. I already know that I have 20 rooms. So there are 20 factorial different ways of ordering these outcomes. So I will just divide this number by 20 factorial to remove the ordering process, because I don't want to look at the ordering process. It's just who is with whom. That's all I care about. Okay, I don't need to know which room they are in. So I'm just going to remove the orders, dividing by 20 factorial. Now this can be done for 20 players as well, because I'm going to try to pack the offensive players together. They are banking together, and I'm going to try to make sure that the 20 defensive players are banking together as well. So I'm just going to pick the 20 offensive players, put them here, and I will start pairing them randomly. Now again, I'm going to use the same strategy, same thing with this one, but instead of 40, I have 20. The multinomial number is 20. So I have this version of it. Now, in here, this part, you can see this is 20 people ordered into packs of 2. But I don't need order once again, because they are going into 10 rooms now. I don't need to know which room they are going in. So I'm going to just divide it by 10 factorial. This is for the offensive players. And the same thing is done for the defensive players as well. We already know that there are 20 of them. I'm going to just pick them by 2 and get them into rooms, but I don't care which room they are going into. So I'm going to have to divide by 10 factorial again. And this multiplication will give me this value. Now, I already know this is the number of outcomes that I want. And the one above, this one I have found, was the number of outcomes in the sample space. All I have to do is divide it by each other. So number of outcomes I want divided by the number of elements in sample space, outcomes in sample space. This is the probability I'm looking for. Now this one, you cannot really simplify. So you can leave it as this. If it's something as complicated as this one, you can leave it as this, but there are some small simplifications you can make. For example, you can just open up these parentheses and simplify those 2 factorials and stuff, but it's just small stuff, it cannot be, it's not going to be a big help in the end, but still it can be done. The second part is more complex. It says that what's the probability that there are 2i offensive defensive roommate pairs. I is going from 1 to 10. So 2i pairs. You can have 20 pairs, you can have 2 pairs. It starts with 2i, I is 1 to 2, 1 to 10. So we have to make sure that we find the number of offensive defensive players first. So let's say that I am picking 2i offensive players and 2i defensive players. In how many ways can I do that? Easy. I'm picking out of 20 offensive players, so 2i out of 20, the combination of 2i out of 20, and the same for defensive, combination of 2i out of 20 again. I have picked my players. Now I want to match them, the offensive and defensives. Okay, there is a very easy way of doing this. Let's assume that the offensive players are set in a line, and I'm just going to distribute the defensive players between them. Now, as the offensive players are set in a line, I can just say that, okay, O1 is standing here, O2 is next to him, etc., etc. D1, defensive player 1, come to the, come to O1 and be paired with him. Okay, defensive player 2 be paired with the other one, etc. Now, this pairing can be changed. I can just change the order of all defensive players, and I will see every other, outcome I can find. And this can be done in 2i factorial ways, because I have 2i defensive players. The offensive players won't move, and defensive players will keep changing them to find all the orderings, all the pairings they can make. And this can be done in 2i factorial different ways. Now, I have this way of picking the offensive and defensive players, this way of ordering them so that they are paired together, and I have non-paired ones left. Now, for example, 2i, let 2i be 5 and 2i is 10. So I have picked 10 players from offensive ones, 10 players from defensive ones, and I have mixed them and I put them aside. Okay, I paired them and put them aside. Now I have 10 defensive and 10 offensive players left. Now, from those 10 players, I have to make sure that all offensive players are paired together and all defensive players are paired together as well. So instead of using 20 and 20 in the first, like we did in the first part of the question, we're going to use 10 and 10. It's the same thing. So if I generalize this to 2i, instead of using 10, I'm actually going to use 20 minus 2i players. So this part, as you can see, is the first part where I have paired offensive and offensive together, defensive and defensive together. This part, on the other hand, is leftovers, whoever is left. I know that I'm going to have to subtract 2i from 20 for finding those people who are left. And again, I from 10, finding out how many different pairings I have, how many different pairs I have. And I'm going to have to just take the square of this because I have two different player types, offensive and defensive. I'm doing this for both of them. This is the same thing we have done in here, but the main difference is we have to subtract the number of players that we have already paired, so which was 2i for both of them. And this is, of course, the number of elements in sample space. So this is this is not going to change. So
Hocam bir soru sorabilir miyim burada?
is the answer for the second part. Yeah, shoot. Let's go ahead.
Burada şu when piki defensive player kısmında
Hı-hı.
2i faktöriyel koyduk ya, tam o 2i faktöriyelin anlamını tam kavrayamadım.
Okay. 2 faktöriyel dedim ya, ofensif oyuncuları tek sırayla tutun. Defensive oyuncuları altında sıraya dizmeye başlayın. 2 tane ofensif, 2 tane defensive oyuncum var, doğru mu? 2 tane ofensif hiç sıra değiştirmiyor. 2 tane defensifin de sürekli olarak yer değiştiriyor. Bu yer değiştirmeyi kaç farklı şekilde yapabilir 2 kişi? 2 kadar insan. 2'yi faktöriyel kadar. Sıra değiştirerekten kaç farklı şekilde pair olabileceklerini buluyorlar. Mesela O1 ve O2 olsun, D1 ve D2 olsun. İyi bir aldım. O1 ve O2 sabit. D1, D2 böyle durabilir ya da yer değiştirebilir. Yani O1 ile D1 match olabilir, pair olabilir. O2 ile D2 pair olabilir ya da yer değiştirirler. O1 ile D2, O2 ile D1 match olabilir. Böyle yer değiştirme sayısını hesaplıyorsun. Bu mesela 2 faktöriyel şey için. 2 kişi için. 3 kişi olsa 3 faktör olacaktı. 4 kişi olsa 4 faktör olacaktı diye gidiyor. Okay?
Hocam şu 20-2 kısmını anlayamadım annem. Onu da açıklayabilir misiniz?
Starting from now, we will see the exam questions, all the exam questions in those exercises. Now, suppose we roll 2 pair dice, a red die and a green die. Let A be the event that the red die shows a 2 or a 5. Let B be the event that the sum of the 2 dice is between 8 and 10 inclusive. Inclusive means they are both included. So 8 and 10 is within our parameters as well for the favorable outcomes for the event B. Now, compute the probability of A. A is easy because event A says that the red die shows a 2 or a 5. So 2 numbers out of 6, 2 out of 6, 1 over 3. Compute B. Now, the probability of B is a bit more complex because we need to find the probability of all the sums of 2 dice. This can be done like this. For example, to get a 12, a sum of 12, you need to roll 2 6s, which is 1 over 36. To get a sum of 11, you need to roll a 5 and a 6, which can be rolled in 2 different ways, 6, 5, or 5, 6. So this probability is 2 over 36. And this goes on like this. So from 1 over 36, 2 over 36, 3 over 36, etc. Till you get to 7, which is 6 over 36. And then it starts falling down again. 5 over 36, 4 over 36. till you get to 2, which is 1 over 36. It actually has a triangular shape. Now, for event B, we need to find the probability of getting an 8, a 9, and a 10, and then sum all of them. Now, getting a sum of 8 is 5 over 36. Getting a sum of 9 is 4 over 36. And getting a sum of 10 is 3 over 36, in which the total of them would make like 12 over 36, which is 1 over 3 once again. Same answer as A. Now, are events A and B mutually exclusive? Now, to be mutually exclusive, they shouldn't have any common outcome. But, for example, let's start with event A. If we roll the 2 with the red die and a 6 with a green die, the total will be 8. So, no, there is at least one common point. And if we find all the common points, which is 5 and 3, 5 and 4, 5 and 5 as well, which makes a total of 4 common outcomes, we can see that this A and B actually have, their intersection actually has a probability of 1 over 9. So it asks us to calculate the union of AB, the probability of union of A and B. Now, we know that this can be calculated from adding the probabilities of A and B together and then subtracting their intersection, the probability of the intersection, which we have already found. So 1 over 3 plus 1 over 3 minus 1 over 9, which makes 5 over 9. And the last question is, are events A and B independent? Now, we haven't seen independency yet, but if we know the formula, we can just calculate it very easily. Independency comes from here. We say that if this is equal to this, then it's independent. Now, we have to check if the intersection of A and B, the probability of intersection of A and B is equal to PA times PB. If this holds, then this is independent. So PA was 1 over 3. PB, probability of B was, event B was 1 over 3 as well. Their intersection, which we had calculated on C beforehand, was 1 over 9, which holds because 1 over 3 times 1 over 3 is 1 over 9. So yes, they are independent, as you can see in the answers here. Question 2. A system has 2 components placed in series so that the system fails if either of the 2 components fails. These system questions are very common. They're especially common in the 3rd chapter, but this is one of those questions which can be answered in the 2nd chapter. So you will have to get used to them as well. Now, if they are placed in series, it means that they are following each other. So if one of them fails, the other one won't work as well. If they were parallel, they were like this together. If one of them failed, the other one would be working and keeping the system running as well. The second component is twice as likely to fail as the first. Now, this is an important part because this is the most tricky part of the question. We have to assume that there is a probability P for the first one to fail, which gives us a probability of 2P for the second one to fail as well. If the 2 components operate independently, and if the probability that the system fails is 0.28, find the probability that the first component fails. Now, the system fails as the first component fails plus the second component fails minus both fail. Why? Now, think of it like this. For the first component, we have 3 different situations for the system to fail. In the first one, the first component has failed and the second one has not. In the second one, the second component has failed and the first one has not. And in the third one, both of them have failed. Now, we can either compute all those 3 situations, which is possible, and then sum them up. Or we can just say that, okay, I'm just going to compute the probability of the first one failing, independent of the second one. I don't know what the second one will do. I don't care right now. And compute the probability of the second one failing, add those probabilities, and then subtract both of them failing at the same time, because we are just using this formula. Now, think of it like this. We are just saying that is equal to PA plus PB minus PAB. We're just using this formula, okay? So this is where the system fails. I don't care which part of this set I am from. I can be in the intersection part, I can be in the B failed part, B only failed part, or I can be in the A only failed part. But I'm in this, as long as I'm in this set, I'm in this event, the system will fail. And this one is a probability of this. So I can just write this one in terms of P, where I already know, and 0.28, where I already have a knowledge of. So let's just write that and see how it happens. Now,
Hocam,
we can say that 0.28, efendim,
bölüyorum da az önceki gibi niye şey yapmadık? Atıyorum 0.28 eşittir P çarpı 2P hani şeklinden independent dediğimizde x'in olasılığını çarpıyorduk yani kök 0.14 niye olmadı?
çünkü şey değil. Sen şu an ikisini birden aynı anda fail ediyorsun. Okay? Sistemin fail olması için bir tanesinin fail olması yeterli. İkisinin birden aynı anda fail olmasına gerek yok. Bak şurada diyor ki the system fails if either of the two components fails. Herhangi biri bozulursa sistem bozulur diyor. Sen ikisini birden bozuyorsun bunu düşünüyorsun. Both fail yapıyorsun.
Tamam, teşekkür ederim.
Okay, so 0.28 our probability of the system failing will be equal to P plus 2P minus P times 2P. Why? Because we know that there's a probability that the first component fails, which is P, and there's a probability that the second component fails. But these events also have the other component failing in them as well. It doesn't have to be like that, but it's just contained in there. So it's contained twice in here. That's just like a set. When you remember the sets, A and B sets, when you take the union of those two sets, if you just calculate the number of elements in them and just sum them without doing anything else, you will get a number of elements that is actually higher than their union most of the time, unless they are, mutually exclusive. So same thing is happening here. We are calculating the probability that the first component fails, but we don't know anything about the second one here. Second one might have failed or might not have failed. They are both in this probability. And in here, we are calculating the probability that the second one fails, but we don't know anything about the first one. It might have failed, it might not have failed. They are both in here. So in both of these situations, we actually have both of them containing the scenario where both components have failed. So we just have to remove it because we need only one of them. So we are removing the part where both of them fail. So we can just calculate the P values here and we get two results, 0.1 and 1.4. 1.4 is greater than 1, so it cannot be an answer. So P should be 0.1. Now this is one way. The another way is that we can just go from the other route, let's say. We can just say that, okay, we are looking for the probability that the first, we are looking for the probability that the system fails, okay, or the probability that the first component fails, okay. We know that there is a probability of 0.28 that the system will fail. Okay, let's just go from where system will work. Because I already know that this first component will fail with probability P, and the second one will fail with probability 2P. Okay, then if both of these work, if both of these do not fail, complementary or fail, then the system will work. Okay, what's the probability that the first one will work? 1 minus P. What's the probability that the second one will work? 1 minus 2P. Okay, I should just multiply these and get 0.722, which is 1 minus 0.28, the probability that the system will fail. So as you can see, this is the probability that the system works, and these are the probabilities that the components work. So 1 minus P times 1 minus 2P should be equal to 0.722. If I just open up these parentheses, I will get the same exact equation that you see here, and same exact result. P is equal to 0.1. As I said, you could have tried the third way. We have a third way here. And you could have just multiplied everything. Let's say P times 1 minus 2P plus P times 2P plus 1 minus P times 2P. And you could have tried equaling this equation to 0.28. You would get the same result as well as a third way. That's also possible. Now, this question is a bit I don't know, not that complex, but a bit, tricky. Ali and Ayşe are presented with 4 different dice. The first one has 2 sides marked 0 and 4 sides marked 4. Okay, these dice are not normal. Okay, they have different markings. They don't have 1, 2, 3, 4, 5, 6 in all of them. But actually, the first one has 2 zeros and 4 fours. The third one has 3 everywhere on every side. The third one has 2 on 4 sides and 6 on 2 sides. And the fourth one has a 1 on 3 sides and 5 on 3 sides. Okay, they're all different dice. So what happens? Ayşe allows her friend to pick any of the 4 dice he wishes. Then she picks one of the remaining 3, and each of them subsequently rolls their dice. The person with the larger number wins $1. Show that Ayşe can choose her die so that she has probability 2/3 of winning no matter which die her friend picks. Okay, it says that we will pick a die, okay, or Ali will pick a die, and then Ayşe will pick one. And Ayşe's die should always be better than Ali's. It should always have a probability of winning 2/3. So we have to just compare all these dice together, okay? For example, start with 1 and 2. Assume that Ayşe has picked the first one and Ali has picked the second one. Now, Ayşe has 0 on 2 sides and 4 on 4 sides. Ali has 3 on every side. So what happens when Ayşe rolls 0? Ayşe loses because 3 will come up for Ali. It's always 3. What happens when Ayşe rolls 4? Ayşe wins. What's the probability of rolling a 4? 4/6, which is 2/3. So if Ali picks the second die and Ayşe picks the first die, Ayşe wins with probability of 2/3. Let's assume that they have picked the dice 1 and 3. So again, Ayşe picks the first one, Ali picks the third one. Now, this time Ali is winning, I guess. We'll see. Okay, the third one has 2 on 4 sides and 6 on 2 sides. If Ali rolls 6, he wins. Ayşe has no chance of winning. So 2/6, Ali will win. But we are not looking for the probability that Ali is winning, so we just will ignore it. We are looking for the probability that Ayşe will win. Then, if Ali rolls a 2, which is 4/6, Ayşe has to roll a 4 to win, which is 4/6 as well. So we'll just multiply those 2 values. And we get what? 16/81, something like that. 16/36, sorry, something like that. So there is a possibility of 16/36, which is like 4/9, that the first die will win over the third die. Ayşe will win. Okay, then let's just take a look at the last die, compare it with the first one as well. Okay, the last die, fourth one has a 1 on 3 sides and 5 on 3 sides. Okay, the first die can only beat the last die if it rolls a 4 and the last die rolls a 1. 4-1. This is the only winning combination, because if you roll a 0, you lose. And if he rolls a 5, he wins. Same thing. So getting a roll of 4 is 4/6, 2/3. Getting a roll of 1 is 3/6, which is 1/2. So the probability of the first die beating the last die is 1/3. We can just reverse this. If the first die has a probability of 1/3 winning over the fourth die, then the fourth die has a probability of 2/3 of winning over the first die. So when we compare all of these dice together, which is, we have to make 6 comparisons, we get this matrix. Now, as you can see here, this is the die Ayşe picks, this is the die Ali picks, and these are Ayşe's winning probabilities. So we had already done for this column. So we picked the first die for Ayşe, the second die for Ali, 2/3, 4/9, 1/3. We have found all of these values just now. Now we are saying that we can just write the complements for this in here, in the symmetrical position. So 2/3, it should be 1/3. 4/9, 5/9. 1/3, 2/3. Okay, we're done with here as well. Now we have to calculate these 3 values, and we can just write the complementaries here. And as you can see, if Ali picks the second die, Ayşe will pick the first die and win. If Ali picks the first die, Ayşe will pick the fourth die and win. If Ali picks the third die, Ayşe will pick the second die and win. And if Ali picks the fourth die, Ayşe will pick the third die and win, with a probability of 2/3 in every one of them. Exercise 4. Now, this one is a bit scary when you look at it, because you are most likely accustomed to thinking in the way you think in high school probability, and you're thinking with decision trees and stuff like that, but it's going to fail here. You'll see. Each of 15 jars containing 5 white and 3 black balls. A ball is randomly chosen from jar 1 and transferred to jar 2. Then a ball is randomly chosen from jar 2 and transferred to jar 3, etc. Finally, a ball is randomly chosen from jar 15. What's the probability that the last selected ball is white? Now, if we try to make it 3 for this one, okay, you have 2 decisions, 2 possible outcomes for each jar, and 14 experiments are being made. 15 actually, if you count 15, but I don't care about this one right now. I'm just talking about carrying over the balls. So 2 to the power of 14, no, you cannot draw it, not possible. So you have to find a more refined way. Let's start with something simple. Let's start with this one. What's the probability of picking a white ball from the first, jar? It's 5/8 because I have five white balls in there and a total of 8 balls. Okay. What's the probability of picking a white ball from the second jar after I'm done with the first one? Okay, after I'm done with the first one means that I have already picked the ball and put it in the second jar. Okay, it can happen in 2 different ways. I might have picked a white ball from the first jar and put it in the second one, or I might have picked a black ball from the first jar and put it in the second one. If I have picked a white ball from the first jar, which was 5/8 probability, then now I have 6 white balls in the second jar. So I have a probability of 6/9 for picking that second white ball. So it's 5/8 times 6/9 if I pick the first one as white. If I pick the first ball as black, which has a probability of 3/8, then I have a probability of 5/9 for picking the second ball as white, because I'm trying to find the probability of picking the second ball white. So when I calculate these 2 values and when I just multiply and add them, I get a probability of 5/8. Wait, this was the same probability for the first jar as well. So picking a ball from the first jar doesn't really have any effect on picking a ball from the second jar. Even if I hadn't picked any ball from the first jar, I would have 5/8 probability for picking a ball from the second jar. And again, after picking a ball, which is something I don't know which color I have chosen, but still I picked a ball and put it in there, I still have 5/8 probability for picking another white ball. So this can just apply to the third jar as well, and 5th jar, and 6th jar, and 7th jar, and 10th jar, and 15th jar. So we can see that the probability will always be 5/8 with all the jars. Simple, because we have shown that it's the same for the second jar as it was the first jar. The third one is just connected to the second one, so it depends on it. The fourth one depends on the third one, 5th one depends on the fourth one, etc., etc. You can take this anywhere, any distance you can go, but still you're gonna have 5/8 probability of picking a white ball at the end, as long as you do not know the previous balls, because if you know any one of them, the calculations will change. That's subject of the third chapter in next week. So what about exercise 5? Let A, B, and C be events such that their union covers the entire sample space. That is, S is equal to A union B union C. Now we know that A, B, and C just spans the whole outcomes. They include all of the outcomes. Okay. If B and C are mutually exclusive, okay, important information. This means that B and C do not have a common outcome. Their intersection is empty set. And A is independent of both B and C. This says that if A is independent of both B and C, we have seen the formula. This means that the probability of AB is equal to probability of A times probability of B. And also A is independent of C, so we also know that probability of AC is equal to probability of A times probability of C. Those 2 will hold as well. And the first one says that probability of B and C is 0 because they are mutually exclusive and they don't have any items at all. So these 2, these 2 parts of information give us these equations. Now, find the probability of PB plus PC, probability of B plus probability of C. Now, we already know that this A union B union C has a probability of 1 because they span, they cover all the sample space. So they should have a probability of 1. Then we will just write this equation. Probability of A union B union C is equal to 1. This can be, opened up as this. You remember this one from the previous lesson, I guess. PA plus PB plus PC, probability of C, minus AB, AC, BC plus ABC. Now, when you look at these values, you can see that this one, ABC, the intersection of A, B, and C, the probability of intersection of A, B, and C is equal to 0 because BC is equal to 0. So this one is equal to 0 as well. Why is this one equal to 0? Remember the set, rules. We can take the intersection any way we want. So we start with B and C, which is 0. So empty set intersected with A is empty set again. Probability of empty set is 0. So these two will fall. And now we have this equation. Now, from this equation, we also know that A and B is independent of B and C. So we can just replace these values with these values. So now we have this equation. Now we will take into common parentheses of A and B, as you can see here. C and B, as you can see here. So when we take into parentheses for the probability of C, we get this value. And when we take the parentheses for B, we get this value. 1 minus PA, they are both the same. And we also have a PA here. Now we are looking for PB plus PC. Okay, let's just start with leaving the probability of C alone. So I have to get these two values on the other side and then divide it by 1 minus PA, which gives me this, and simplified version this. Now, as you can see here, this and this are the same thing. 1 minus PA, 1 minus PA. So they can be simplified. But there's an important thing to not, miss here. When I simplify a denominator with a denominator and with a numerator, whatever, you have to check and make sure that they are not 0. If these values, if this value is equal to 0, then you cannot simplify it. Then it's just 0 as well. It's not simplifiable, let's say. So as long as these are not 0, you can get a clear answer. For this one to not be 0, PA should not be equal to 1. So PA can't be equal to 1. So when you simplify this, you get 1 minus PB. Now you can see probability of C is equal to 1 minus probability of B. So probability of B plus probability of C is 1. They are mutually exclusive and they span the sample space. So they are actually covering all the outcomes together. And they don't have any common points as well. And exercise 6. Now this is...
Hocam peki A'nın 1'e eşit olmadığını nasıl anlayacağız? Bu soruda nerede belirtiyor?
Bu. A 1'e eşit değilse. This is an assumption. This can only hold if this holds. If A is equal to 1, you cannot say anything about this. They can be anything.
Anladım.
If A is equal to 1, this has infinitely many solutions. They can be anything. But as long as, or maybe they don't have any solutions. Maybe they're infeasible as well. It might happen as well. We have to check. But still, as long as PA is not equal to 1, this one has a solution where PB plus PC is equal to 1. The heads of n persons are thrown into a box. The persons then pick up their heads at random, so that every assignment of the heads to the persons is equally likely. What's the probability that every person gets his or her head back? Now, we are just removing our heads and throwing them in a box. Then I'm the first person to pick. I'm going over to the box. There are n heads in that box. I'm not sure which one is mine. I'm just picking one at random. Now, my probability of getting my own head is 1 over n, because there are n boxes and n heads in there. So one of them is mine, 1 over n. I took it and I'm going back. I've got mine. The next person goes in there. He or she wants to take his own head as well. So what's the probability of him getting his own head? There are n minus 1 heads left, and one of them is his, so 1 over n minus 1. He lives. Another person comes, she wants to pick her own head as well. There are 1 over n minus 2 heads left. So there are only n minus 2 heads left. So her probability is 1 over n minus 2. And it goes on like this till the last person, where there's only one head left, and it's her head. So she just goes and picks it up. So when you think of this as n different experiments, you will just multiply all of them. 1 over n times 1 over n minus 1 times 1 over n minus 2, etc. Which gives us the probability of 1 over n factorial. Simple. The second part, the first n persons who picked heads get their own heads back. Okay. The first n persons will get their heads. The rest, we don't care. They can get anything they want. Okay. So when you consider it like this, we know that we're not interested in the other ones. So we already know that there is the sample space is n factorial. N factorial different things can happen in there. Okay. Each person can be matched with another head. So there are n factorial different ways of getting heads. Not your own head, but heads. In only one of these, everyone gets their own head. So it was 1 over n factorial in the first part. Now in this part, we have n people getting their own heads. The rest, n minus n people, can get any head they want. They might be getting their own heads or someone else's head as well. So they have n minus n factorial different ways of getting heads as well. When you just, get their, divide them by each other, you get this one. Because now, n minus n people, think of it like this. There are n minus n people here and n minus m heads, or n minus m heads left here and n minus n people. They can get different heads every time. They can just keep switching places. They're just being reordered all the time. And the number of times you can reorder them is n minus m factorial. What about C? Now, there's a little change in the question here. Now assume, in addition, that every head thrown into the box has probability P of getting dirty, independently of what happens to the other heads or who has dropped or picked it up. Now, our heads are getting dirty. We're just throwing them in, and they're getting dirty with probability of P. We don't know which head is dirty. We don't know if the head is dirty unless we draw it back and see it. But they're in there, and they might have been, they might have been dirtied, whatever. But the first m persons, we are looking for the probability that the first m persons will pick up clean heads. Now, the probability that clean head is coming up is 1 minus P for everyone, because we don't know how many heads are clean in there. We just know that each head is independently of each other, has a chance of getting dirty, which is P. So staying clean is 1 minus P. So the first person, when he or she goes to the box and picks up a head, has a 1 minus P probability of getting a clean one. Then the second one comes, same probability, 1 minus P. Then the third one comes, 1 minus P. Till the nth person, he or she still has 1 minus P probability. So the probability we are looking for is 1 minus P to the power of m. Exactly m persons will pick up clean heads, part D. Now, exactly m means that, in the first one, we didn't care about the rest of the people, so they could have picked up anything they want. The first m people were picking up clean heads, the rest can get clean or dirty, it doesn't really matter. Their total probability will be 1 anyway, so it won't matter for us. But here, it's different. Exactly m persons will pick up heads. Okay, let's start with m persons picking clean heads. Let's start with m persons picking up clean heads. It's the same. 1 minus P to the probability to the power of m. Then the rest of them, the n minus m person, will pick up dirty heads, which is P to the power of m minus 1. But still, these are two probabilities. Okay, we are good there, but still there's something missing. We don't know who is picking which head. Okay, we know that the total number of clean heads picked up is m, but we don't know who picked up those clean heads. We have to pick the people as well now. So we're just going to use the combination formula for this one, m out of n. Now, this here is the probability of getting m clean heads. This here is getting n minus m dirty heads. And this is the people who are getting, the number of people who are getting, choosing the way of choosing the number of people who are getting the clean heads. And the last exercise. This is actually a question from one of the assistants, which I loved, by the way. It was a very nice question, I think. We'll see. 2 dice are thrown in n times in succession. Let x be the event that double x's appear at least once, and y be the event that double x's appear at least twice. Compute px, compute py. How large n need be to make px at least 1/2? Let's start with the first one. Compute px. Now, we know that x is the event that double sixes appear at least once. Okay, and we are throwing these dice n times. Okay, the probability of getting 6 double sixes is 1/36. We already know that. So if it's gonna appear at least once, I need to make sure that I can calculate it because I have n times. I'm throwing n times. I don't know the number n which value it is. So it can be 1,000 maybe. I cannot just go over like this. Okay, I'm just gonna calculate the times that double sixes has appeared only once or twice or 3 times or 1,000 times. I cannot just enumerate them one by one. Instead, I can think of it like this. Okay, what I want is the double sixes to appear at least once, and then what I don't want is for double sixes to not appear at all. Okay, if I find the probability that it doesn't appear at all, I can just subtract it from 1 and get what I want. So for double sixes to not appear at all, every row has probability of 35/36. So what I need to do is just take the nth power of 35/36, which will give me no double sixes in every trial. And then I will just subtract this value from 1. So 1 minus 35/36 to the power of n for the first one. The second one, now in here, for py, the event y is double sixes appear at least once. So now he doesn't want double sixes appearing once or never. Okay, anything else is okay. We already know the never part, 35/36 to the power of n. Okay, we need to find the once part. Okay, same as the heads, last part of heads. We need to pick one of the rows and make sure that this is the double sixes, this is where double sixes appears. So it's 1 out of n, combination of 1 out of n. And then we are going to have to find the probability of getting that double six, which is 1/36, one time. And then we have n minus 1 times no double sixes, 35/36 to the power of n minus 1. And this will be subtracted from the previous one as well. As you can see, we are subtracting from 1 the times that the rows that have no the experiment or that has no double sixes, and the experiment where only 1 double six appeared. These two scenarios are the ones we do not want because we want double sixes to appear at least twice. So we are subtracting their probability from 1. The third one, how large need n be to make px, the value we have found in the first one, at least 1/2? Now, as you can see here, for the first one, as n grows, okay, this value gets smaller. As this value gets smaller, this part, the px, gets bigger. Because if n was 0, which is not possible, but just roll with it, then this value would be 0 as well, because this will be 1. 1 minus 1 is 0. When n is 1, this is 1/36. When n is 2, this is probably somewhere between 1 and 2/36. And it grows, keeps growing. As n grows, this value grows as well, because this is getting smaller. The minus part is getting smaller. So it says that you want to make px at least 1/2, find the value for n. Well, there are two ways of doing this. Just write it in a calculator and try. It can be done because you don't need to do it one by one. You can just start with 10, then try 20, and then go up or down depending on how you are doing from there. Or you can just use the logarithms in here. Now, as you can see, we know this value. We want this value to be greater than 1/2. So we just simplify 1/2 with 1. So we want 1/2 to be greater than this value. We are just moving this part on the right-hand side. Now, we want 1/2 to be greater than 35/36 to the power of n. We just take the natural logarithm for both of them. We just log them, 1/2 and 35/36. Now, this n, as it's a power, comes down as a coefficient. Now, from here, we can see that we can just leave n alone and take log 35 over 36 to the other side, we can see that this has to be less than n. Okay, why is this less than n? Why is the greater sign changing when we are taking this one to the bottom side? What's happening here? Log 35 over 36. 35 over 36 is what? Less than 1, right? So this value will be what?
Negatif mi?
Negative, exactly. So that's why when you're moving this one here, this sign will change. Many students have, not many, but most of the students that have tried this logarithm way have failed to notice this sign change, so they have lost some marks here. But this is an important part of mathematics, so you have to make sure that you do not miss stuff like that. So from here, we can see that n is greater than 24.6. So we should do at least 25, experiments to make sure that this is at least getting a, probability of 1 over 2.